Is one I'm really looking forward to. It was about, 6 months ago, I was talking with Michael Steinbacher at the Electric Universe Conference, and I discovered, for the first time, at least to me, that you could actually zap dust with electricity and create rocks. I just thought that was the coolest thing ever. So apparently this actually has been done in the laboratory, and Paul is excited to get down and dirty and start doing some work in this very area, and he's going to be talking about some work that has already been done and is well on his way to doing, I think, an incredible project in this area. Just the idea of geology as it's created in terms of electrical events. So I'd like to welcome Dr. Paul Anderson.
It's gravity for you right there. Proof of gravity. Well, thank you very much. It's a pleasure to be here, and I'll be talking about electric scarring. So, a few years ago when I got turned on to the Electric Universe and reading Stephen's wonderful blogs and teapods, seeing all these beautiful landforms with scars on them, I said, that's great, but I'm a chemist. Not a geologist by training, but I am a chemist, and I like to prove things. So I said, is there really a way to prove this? Is there a way to quantify it? Because that's going to set us on the path to further study this effect. So this is an introduction here. I'll give you a minute to look at these pictures. These are three different pixelated pictures from three different scales of events, of electrical events. We call these things witness panels where I work, but basically these are all witness plates to an electrical event and a discharge across a dielectric. One is the Grand Canyon, one is polycarbonate, and one is concrete. So I won't quiz everyone here, maybe make your choice. Right. And there. Did anyone get it right? No. It's kind of hard when they're pixelated like that, right? So what the pixelation is doing is it's highlighting the channels. I've grayscaled it and I've pixelated it so we can actually quantify the various regions of the channels. So it's really interesting here that the Grand Canyon looks a lot like these other discharges. Very easy for us to say. And in fact, back in the 80s, late 80s, when Mandelbrot started put out his book, Fractals in Nature, I believe it's called, he was a mathematician that famously brought about this Mandelbrot set. You zoom in, wherever you are on this set, you zoom in and it repeats itself. That's called self-affinity. That's a fractal. It's a power law. And interestingly enough, electricity dielectrics, or electrical discharges across dielectric and electrical discharges themselves exhibit this behavior. So I said, well, maybe there's some sort of way to quantify this with electrical discharges. And indeed, you dig into the literature, especially the IEE literature, and there's plenty of articles on this, because in industry, this is a very important problem. They need to quantify the amount of dielectric discharge across wires or insulators, whatever it may be, so that they can prevent this. People are also making lots of money off it, making these beautiful figurines across polycarbonate, and that's where I got that picture from. So they strike a charge on a glass of polyacrylate or polycarbonate. The discharge occurs across the entire block, and you're left with this beautiful Lichtenberg pattern. So I'm wondering if there's any way we can now quantify things on a geological scale, on an Earth scale. If indeed these events, if indeed, say, the Chesapeake Bay was not carved out by just years of erosion, millions of years of erosion, indeed if it was carved out in an instant by an electrical discharge. That's the question. And in a geological community, they're going to ask, well, show me proof. Okay? So is the current geological paradigm missing something? I believe yes, and hopefully we'll find a way to quantify that. So the objectives of this study was to determine if certain landforms, however they arose, either from glow discharge, arc discharge, we don't know yet, occurred from electrical discharge rather than fluvial erosion. That was the goal. So we have to find a way to quantify that. And so that's where I use the fractal tool methods. And really the simple assumptions here for this study, I assume that things in the past were not as they are now. There were catastrophic discharges. However, the electrical environment of the Earth changed, but it was definitely more than the current income charge plasma, whether that be from a planetary encounter or sun, we don't know. And these events occurred over large scales of land. I included a slide on the plasma universe theory. I'm sure you'll hear more about it soon, and the previous speaker just talked a little bit about it too. I drew these from Altman's paper back in 1990. I'm sure other people could add or subtract from these, but in a basic sense, the same basic laws of plasma physics hold throughout the universe. So when we encounter a highly charged plasma here on Earth, the Earth is going to react the same way Mars would react or other places. But we just have to know that electric field distribution, and that's a current challenge. That's a current challenge. Space, we know, is filled with this filamentary and cellular structure because of that plasma. And these double-layered and pinch effects, as I'm sure you'll hear in other talks, are central to our understanding of how this matter is formed. Also, it may contribute to the surface geology that we see here. This is just a smattering of papers that I used to find how fractals are used in the electrical community to quantify, or at least semi-quantify, the results from electrical discharges. So they can actually rate the fractal dimension of these electrical discharge and try and find some qualitative differences between different insulation materials. But the take-home message is that indeed you can use fractal analysis for the study of these events. So folks from the Tesla Tech here, I'm going to learn a lot from you tomorrow night, okay? But in a very simplified fashion, if we think about some sort of dielectric between two charged plates, eventually that dielectric will break down depending upon the parameters and depending on how much voltage you put across that. And when that does happen, you have a series of responses. You could have magnetic fields induced, you have current, you have some sort of light and or heat, you have your actual electric arc path. You may even have nuclear interactions, possibly transmutation. That's been talked a little bit. That's been talked about a little bit. But the factors that cause that, in any of those previous papers that I showed on the slide, they talk about these. There are a lot of factors involved. Geometry of your electrodes, what type of dielectric, what the current is, what the power is, even the microscopic plates or the microscopic surface topology of these plates will affect how your electric field distribution occurs and eventually when it breaks down. So there are a lot of factors at here, and that's why it's important to keep that in mind when we start experimenting with this. So we need to do a due diligence in our design of experiments. So now I'm going to move on to geology. Why are there picture of tracks with mud? Really, the take-home message here is once you imprint something on the Earth, if water flows into it, you can see that. You can see the imprint of that Earth. Now, if water keeps filling this, you're not going to see that. As it drains, you might see other evidence of different aspects and resolution of that tire tread. So you see evidence of that on the Earth a lot. This is up in Alaska, where you see a downhill slope. You see spreading alluvial fans as you come out on the plain, less slope. You have a water source which is carving these channels in the slope. And every year it happens because every year this gets deeper and deeper. That can be quantified, measured, everything like that. There are also other examples on the Earth where that does not occur. I think the best examples are actually found on other planets, namely Mars. And if you look here, it's opposite. So the problem here is that if you have some sort of water flow, and that's what most NASA scientists believe, and you're going downhill, your alluvial fans actually increase as they go uphill. So something's happening here because this is the edge of the crater here, this is the crater downward. There's obviously some other mechanism at play here. Okay? So alluvial fans tend to increase in their width and their breadth and their sediment carry and sediment load. This has all been measured by geologists, pretty well characterized. The problem I had with this study is that there aren't many fluvial events per se that you can quantify. I found a handful of them for this study, but usually what you find is something like this. This is Canyon Lake down in Texas, and if you pixelate it like I did before, you get a very linear type pattern. There's very little branching, even though this is just a very gentle slope here. You would expect this to branch out if it was able. In the same way, Mount St. Helens, I do have the Google Earth copyright on the last slide. If you look at the terrain map of this and then you digitally pixelate where the pyroclastic flow went down the hill, you have very little branching coming out. So then we can take these patterns, pixelate them, and perhaps quantify them with fractal analysis. Now I have a question mark in here because then I was looking at other lakes and whatnot. This is Armistead Lake in southern Texas. And what struck me about this is it's a dammed lake. It was formed in 1969, I believe. So they started backing it up in 1969. So any landform patterns here were formed by previous events, whether they be fluvial or electric, right? So once you digitally pixelate this, it's a very, very different landform that's being highlighted by the water. So the water is actually filling up the levels, and you actually see handprints, fingerprints of what was there before. Again, whether it's fluvial or electrical remains to be seen. I tend to see dendritic patterns here, telltale of an electrical discharge. Slightly biased, but you see the same thing along the edges all the way up and down the Mississippi River. This is in northern Mississippi. You see the Mississippi floodplain very evident in the current Mississippi, or one branch of it. And then the hills right next to it have a very chaotic and stochastic dendritic patterns. They don't have any rhyme or reason for a fluvial drain-off. If you look at the elevation of these in whatever direction they're going, it doesn't make sense that either the Mississippi River flooded and then came back into floodplain, or a previous flood happened. There could be tectonic events, there could be something underneath the surface of the earth, but something made these occur before this fluvial event of the Mississippi. So if we move forward to electrical patterns, what we can find are these telltale signs. These are from some of the literature articles that I showed before. Typical dendritic patterns here. And these actually go on to infinity. If we can increase the magnification of the microscope to infinity, we'd see ever more branching patterns. This is a transformer that let loose, and you can see the discharge pattern across their insulation material. So again, so now we got to measure these things. We have a collection of materials, a hypothesis. Maybe we can use fractal. So a fractal is defined as a self-similar setter pattern. It's a power law. So they are the same as they are near as they are from far. That's a basic definition put out by Monte. Now electrical discharges are known to be self-similar, as I mentioned that before. The literature shows that. Now fluvial systems, reading on those, really the only fluvial systems they've done a lot of fractal measurements on that are fluvial systems on their own. In other words, floodplains or braided channels. They all exhibit self-affinity, and that's slightly different than self-similarity in that they're only similar in a certain direction, i.e. the direction of flow. That intuitively makes sense to us, right? So confined river networks, though, the geologists have a hard time with, because the fluvial aspects of these rivers are dictated by the actual surroundings. So already we're confounding our hypothesis, because either those surroundings were there first and then the river came, or the river caused those surroundings. So that's a hard thing to investigate if you're investing something that happened in the past. So I'm wondering if we could tell this amount of dissimilarity, at least between these different types of fluvial systems versus supposed electrical discharge systems. So how did we do this? I took the images, I now analyzed them in ImageJ software. You can download that from NIH. Your fractal dimension is there embedded in the software. It uses the basic box counting method, which is the common method to assess the fractal dimension. That's valid for projections of things into 2 dimensions. As long as your fractal dimension is between 1 and 2, that's valid. Here are some image data. I tried to keep the mileage about consistent, right? So we can compare images to images. Now, the topography was ignored. I mentioned that up here because even in studies of electrical trees, they're 3-dimensional. But the electrical engineers found that the maximum you can get for a projection onto a 2D plane is 1.7. And indeed, that's what I found. I found all these electrical discharge patterns topped out at 1.7. So the data looks good from that perspective, and I'll show you that in a second. So some definitions here. Whenever you see fluvial on the graph, that's from fluvial events. Either braided river channels, floodplains, the canyon lake event, Mount St. Helens. We know those are fluvial, we observe them. Electrical events are from known electrical events, either polyacrylates or discharges or small-scale lab tests. And then the unknowns were just from canvassing the whole Earth, capturing these Google Maps, and assessing these landforms that look to be very highly fractal in nature. This is how I process the image. This is an image from up in Oregon. You see the canyon, the steep canyons, and the fingers, the dendritic ridges. So the first fractal test that I do is just for a straight pixelation, and you get a fractal dimension from this equation. Again, it's power law. Now I then take it one step further and I skeletonize it. By doing that, you're eliminating any topological effects. So in other words, what I'm doing is I'm only measuring the branching associated with this main branch, and this main branch, and this main branch, and this main branch. So effectively what you're doing is you're removing all this excess data here. And what you're able to do then is effectively measure the amount of branching. Upon further reading, I know the box counting method is not the best way to do this, but it has been done in the literature. And so what data do we get? You can see a limited number of data sets. I have this in the end if you want to see the data sets. I was only able to find like 8 fluvial events. I was able to find a good number of electrical events. Obviously with Google Maps I can find a lot of landforms to analyze. So what this is like a statistical significance test. It's similar to the student's T, if that rings a bell, where you're measuring the population or the measurements of your population and you're seeing if they're the same or not. This is a slightly different test because it takes into account the different population numbers. Okay? So we can do some statistics on here, and basically wherever you see an overlapping circle, they are not statistically dissimilar. So when we just do our basic D analysis, or dimensional analysis of that first river formation, everything looks about the same. You don't see any statistical dissimilarity. All right? But when we skeletonize them, that's when the branching comes out. And that's when we see the differences, the bare bone differences in these patterns. This circle is associated with the fluvial event. It is statistically dissimilar from both the unknown geological events and the electrical events. However, you can see that the two circles overlap each other with the unknown event and the electrical event, which means that they are statistically similar in fractal dimension. And if we therefore draw the conclusion that this fractal dimension is a measure of the origin, it's more like the origin of an electrical discharge in the fluvial event. So, some people will say that's not enough data. Okay, well, because I do this on my own as a hobby, such as being a scientist, right? I basically took these and did a Monte Carlo distribution, or a Monte Carlo simulation, which takes a pseudo population set of this and makes a normal distribution. I assume a normal distribution. And then what I can do is say, okay, well, with that normal distribution, let's look at the statistics again. Let's say I had a grad student that could do this for a full year, and they get 300 data sets, and let's see the statistical significant difference. And indeed, we get the same thing. We see that the fluvial skeletonized is indeed much more different than both the unknown skeletonized, or the geological landforms that I looked at, and the electrical events. So in other words, the landforms are more similar to the fractal dimension of an electrical event. I didn't mention before too much, and I should have, that electrical events are scalable. And Don Scott talks about that in his book, and others have talked about in their articles. It is scalable down from the micron size, micrometer size, all the way up to galactic events. That's something about electricity that is working in our favor, because we can do laboratory experiments and then logically scale them up to some extent. It's not the same for fluvial events. It's very difficult to do large-scale fluvial events in a laboratory. Materials do not behave the same way in water on a small scale and a large scale. Okay? So again, just increasing the population, that's one of the tools we can use to look at these differences. So furthermore, if you want to look at the numbers and the statistics, the larger number denotes less similarity. So if you look at fluvial event, electrical event, and unknown event, the two numbers for the unknown and the electrical are more similar, and you see there's a large number for the fluvial. Okay. So the significance is profound here, and this is just on a cursory data set. So I believe at this point, morphologically at least, the conclusions are that many of these geological structures do arise from a potential electrical event. In other words, it's more like an electrical event formed these than it would be from a fluvial event, at least the data that I have on fluvial events. So when we look at the EU concepts, it may be a more powerful way to describe what we see in geography. Okay? If you're interested in seeing what other materials I looked at or what regions of the Earth, just contact me and I'll give you my URL to the Google map that I'm slowly populating. But I recorded all these areas that I took and then used for this study. And I also have them listed in the appendix, I think, in my tables in the paper. Now when I say future work, this is what I hope to do. Obviously, augmentation of the current data set is important. When we get around to actually doing the discharge experiments, we're not just going to zap rock. I think, and that's a good first start because it shows utility. So I think it's important to start there to get your boundary limits, and I know a number of people have done that. So that's very important to start off with. But now the second step is to really determine its feasibility, okay, and also its capability. And the way to do that is through statistical design of experiments. And this isn't just sitting down and saying, I'm going to do this, this, and this. It's actually letting statistics do the work for you. And in doing so, we first have to down select the factors we want to look at. Once we have a down selection of factors, and we get that from the literature search, from what people have already done in the lab, we then select our factors, we design our experiments, and then we decide what we're going to look at. And I think what we can do very easily in the lab is we can obviously look at changes in hardness from a certain sample. I think we're going to have to press the samples to make them a hard surface and then look at the hardness change. We can look at the chemical constituents and other tools in the lab, like X-ray diffraction, which can tell any changes in the mineralogy. So the chemical and physical composition of the rock or soil that we use. From a lot of reading of past events, I think water is going to be an important part of this. And that's going to be challenging with electrical events because what I've talked to people about, it can be very difficult to do that, especially if we're using a high vacuum chamber or a vacuum chamber. So this is just a new way of approaching not necessarily a problem, but to try and experiment so that we get a response that we can then model. Because remember, once we have a model, we can then scale up, and then we can do further experiments. So I just want to acknowledge a few people, obviously my wife, because she let me sit there and analyze these fractal patterns. And so she dealt with my hobbies. She deals with a lot of my hobbies and pursuits, so I really appreciate her support in this. Bill Davis is the person that really turned me on to EU, so I always throw my thanks out to him. A number of years ago, he started talking to me about it. And one of these days, he'll make the meetings. And then obviously Mike and Monte for their comments. So I appreciate your time, and I'll be happy to answer any questions.
We've got plenty of time for questions, so please come up. And while we're waiting, I'd just like to make a comment and say I am so excited about this work, and I'm so glad you're here, because this is just cool, and I think that what you're doing is just a tremendous example of what we need to be doing, and you're going about, you know, you've got a hypothesis, you're collecting data to support your hypothesis, and then you're following it up with experiments to prove the hypothesis, and that's exactly what we're supposed to be doing. So thank you for being a good example to all of us. And no other questions? Oh, come on up, please.
I'd like to share Greg's comment. One of the nice things about, I think, what you're doing is you're quantifying. You can say, well, this looks like that. And somebody says, well, yeah, but you can't, just because this looks like that, you can't say that they're the same thing.
Right.
I'll be talking more about that in a minute.
Yeah.
But you're putting numbers on it, and I think that's very, very valuable.
And it's interesting you mentioned that, because Mandel brought that up early on in his fractal analysis. He said that many things from trees to electrical patterns in shorelines have the same fractal dimension. Does that mean a tree formed a shoreline? So we have to be careful in how we interpret fractal dimensions, and I'm fairly new at that. So if anyone is familiar with measuring fractals, please come talk to me, because I want to make sure we're using the tool right. So that's a very good point. So.
Yes, and thanks, Paul, for doing this, because this is something that's has been on the list, or wish list, for someone to get in there and put the numbers to it. And what I'd like to see, what I see your work as doing is laying a foundation that others can build on, using the same kind of fractal analysis for dendritic structures on the sides of the cliffs, for the repetition rates of certain geological features, like the outcroppings along the Grand Canyon or things in the Monument Valley. And so it can be extended not just for flat topography, but also for on the sides of things. And look. So I see this going to a lot of different places. I guess that wasn't a question.
Okay.
Do you?
Well, along those comments, and I think the geological community is already using these tools. So that's something else to tap into, is to make sure we have access to the literature and possibly friends in the geological community that would be interested in helping us with this, because they have measurements on 3-dimensional fractal analysis and just what you're saying.
Okay.
So it's out there. I encountered it, but again, it was above my learning level, and I couldn't interpret a lot of the 3-dimensional aspects of it.
And of course, we want to see it done for Mars too, of course, which is kind of the Rosetta Stone.
I was tempted to go there, but I was like, you know what, I'm not going to go to a different planet for this analysis. It's another factor entirely. So, all right, thank you.
Oh, I have one more question.
Sorry.
Fractal patterns that you showed have an orientation to them which signifies where the source is for that pattern, or at least that part that you can still see. It would be good to try and identify what the sources appear to be like. In other words, is there anything that's in common from one fractal pattern to another that can be identified with a source? We say it's electrical, but can we go more than that? Can we say anything about the nature of that electrical discharge?
Well, I don't know if I have time for the backup slides, but actually Forrest has done some calculations as well as I do, and actually we came to very similar conclusions about the energies involved about removing all the rock for the Grand Canyon. But in terms of where that discharge occurs, that's a good question. Mike and I were just talking about, there seem to be very large catastrophic events, and these discharges actually occur on the periphery. So I don't think these discharges are like putting a needle onto a dielectric and zapping it right there. I think there's something else involved. I don't know what yet. But they seem to be on the periphery of craters on Mars. You can look at craters on Mars, and they're always on the periphery. They're never like right where seemingly a discharge occurs. Whereas in a laboratory, when they're studies in a laboratory, they lower a needle down, and the discharge usually occurs very close to that needle. So maybe it's just kind of an order of magnitude of resolution thing that we're looking at right now.
Well, anyway, I think that's an important issue.
Okay.
There's a great, there is
A board wetted with salt water and 2 nails on YouTube. Terrific video. Right? Hit it with the electrodes. I think it's make 10,000 volts, and you can see it looks like Val Marinaris going on, and you can see the time evolution of this. It isn't just a zap at a point like the lightning strikes and whatnot.
Okay.
And it evolves over time and branches and even makes crisscross patterns. It'll go one way and it'll crisscross that way. All kinds of things going on this board. So I think things like the Grand Canyon could be that where there's telluric currents involved too. It isn't simply just coming down from the sky. There's things coming in underground over a period of time.
All right, thank you very much.